So in last class, we learned about the two-stage algorithm for the object detection. Okay, that those are RCNN, fast RCNN, and also the faster RCNN. And also after that, we learned about the YOLO algorithm, which is the one-stage algorithm. And in here, you will estimate the bounding boxes and also the class probability for each grid at the same time as this array. I mean, this kind of vector for each grid that is represented as the 7 by 7 by 30 dimensional array. Okay, because there are 7 by 7 grid. This 7 by 7 denotes the number of grid, and this 30 dimensional vector, it is denoting we will estimate 2 bounding boxes for each grid and also 20 classes probability vector we will estimate. So it depends on some hyperparameters of our problem. So if the number of classes that changes, or if we set to estimate more than 2 bounding boxes, or if we change the number of grid, then this, the dimension of the array will be changed. Okay, are you following this? Okay. And also I explained what the 5-dimensional information that constitute the bounding box information is. How they are composed. I explained it here. And 4 is for XY center position and width and height of the bounding box. And 5th, that's the confidence value that denotes if this bounding box estimation is correct or not. And also it reflects that grid is having object or not. Okay. Are you guys following this? And after getting this amount of bounding boxes, actually we get 98 bounding boxes from the overall images. And then we have to, when you get the bounding boxes, then that would be like this. For the same object, lots of bounding boxes are estimating the same object. So we have to somehow filter out the best bounding box among them. Okay, so that is the algorithm called as the non-maximal suppression. Basically, what this is the code for that, and basically what they do in the non-maximal suppression is when 2 bounding boxes are highly overlapped, which means if they have high IOU values between them, then we will select only the one with the higher confidence value. Okay. So with this algorithm, we can select the best one that describes the object. Okay, and also this was the loss function, and basically it closed the XY center position and width and height of the bounding box, close their ground truth, and also we have to make the confidence values have the proper prediction, and this is the loss for the class probability. So that's the YOLO algorithm. And the original YOLO is quite fast, but their performance is limited compared to the 2-stage algorithms in here, RCNN, fast RCNN, and faster RCNN. But when version is up, nowadays we have YOLO version 11, and if but YOLO version 2, it improves the weaknesses of the YOLO. So its performance is already better than the RCNN and also the fast RCNN. And some variants for this YOLO version 2, it also surpassed the performance of the fast RCNN. Anyways, this is so now in industrial environment, because YOLO is very fast and it's very practical, and also it exhibits very good performance. So in real world situation, we are many many engineers are using this YOLO for train object detector for their own problem. Okay? And one of the weaknesses of the YOLO compared to the fast ICNN or in overall the ICNN stream algorithms is they exhibit very low recall. Okay, so because YOLO predict only 98 bounding boxes, so if there are more than 100 objects inside an image, then we can miss necessarily missing 2 objects because they estimate relatively less number of bounding boxes. I mean, if we you remember that in RCNN we estimate this amount of bounding box candidate from an image. Are you guys remember this? Okay, so among them, maybe the true object will be one of the bounding boxes, but YOLO is estimating small number of bounding boxes, so there becomes high probability for missing the real object, okay, from an image. And I already say you the difference between recall and precision, right? So this is actually very important, and I will be raised one quiz problem from here. Okay, so you have to remember what's the recall and what's the precision. Okay, so precision is calculated like this. So among the output, the system outputs, how many samples are correct? How many outputs were correct? That ratio is precision, okay? But the recall is, there are maybe n object inside an image. Then how many objects out of n objects are covered? That's the recall, okay? So the system have to cover all the objects or n object, but if the system miss some of the object, then the recall decreases. Okay, I agree with this. Okay, so the good system, it have meet high recall and also the high precision. Okay, so if we if we measure only the precision, then this kind of thing happens. I mean, that happens for developing YOLO 1, actually. So the system works very well when it produces the output. Okay, so that's because the precision is high, okay, but it cannot cover all the object inside an image. Okay, so because YOLO predict only 100 bounding boxes, it may miss some of the object which is in an image. So it exhibits low recall, but among among these 100 bounding box, also we will filter out unnecessary bounding boxes using NMS, the non-maximal suppression. So the final output of the YOLO, it would be precise, okay? But YOLO may miss some of the object in an image. So that's why YOLO is exhibit low recall, okay? Compared to the precision, YOLO suffer from achieving the good recall, okay? So in YOLO version 2 and 3, the author try to improve this aspect. Okay, so we will also see that in the later lectures. Okay, so that was the thing we learned last class. Okay, and we will actually continue to learn about the object detection pipeline. Okay, from this class. So, but the thing is, nowadays, so far we learned about the CNN architectures. Okay, so mainly its operation is composed of the convolution operation. Okay, so from for the input image, we apply the filter kernel in the sliding window manner and output some output maps, and each pixel of the output is obtained by multiplying the filter coefficients with the pixel values, and by adding them, we can get one pixel value of the output map. Okay, are you guys remember this? Okay. How we calculate the the output of the convolutional operation. This is the input, and by applying some filter corner, maybe this is very small compared to the original image. And if we apply this on here, we multiply these filter coefficients with the pixel values on this location. And by adding them, we calculate one output. And we remove this filter corner by the stride size and calculate the other output pixel and so on. Okay. You remember this, right? This is the main component of the convolutional neural network. But nowadays, people are more and more use the transformer architecture. The main operation of this transformer is called as the self-attention. Anyways, the attention mechanism. So instead of the convolution, we mainly use the attention mechanism as the main operation. This attention mechanism is also differentiable, so it can be used inside the deep learning architectures. Okay. And so, now we will first learn about this transformer, their main operation, the attention mechanism, and then we will see how we can make the object detector using this transformer architecture. Okay. Because nowadays the transformer is very popular, so you may heard about the GPT. Okay, ChatGPT. Have you heard about that? Maybe it's fast. Maybe to check if there's a person who didn't heard about this GPT, right? So GPT is very popular today. GPT, their word, is the abbreviation for this generative pre-trained transformers. Okay, GPT is also constituted with the transformer their operation. Okay, main operation of this transformer is the attention mechanism. So GPT is actually using the attention as the main operation. And also before GPT, this is made by OpenAI. And before this, they also made the BERT, B-E-R-T. This is also the abbreviation for bidirectional encoder representation from transformers. Their main architecture is from the transformer. Okay, so maybe seeing this, you may feel that now transformer is actually very popular. Okay. Okay, and also this transformer was first proposed to deal with some natural language processing problem, which is the the sentence translation. So from the English, if you want to translate the English sentence to the French sentence, for example, for that, they use this kind of the transformer. They developed the transformer architecture first. And then we extended to nowadays the image domain for the object detection or other computer vision problems. And we observed that this transformer, their attention mechanism is actually better than convolutional operation. So we are now actively using this operation. Okay. Okay. So when explaining the CNN, I already told that we are using this convolution because it is differentiable operation, right? But there's no guarantee that this operation is the best. Okay. We are using this because we use the filtering operation. This is convolution operation, but frequently referred by the filtering operation. And this filtering is frequently used when processing the images, 2D images. So when you use the Photoshop, there might be a lot of filter, right? Blur filter and sharpening filter and others. Okay, that kind of filters are defining filter kernels that can transform images according to their functions. Okay. Anyways, they apply convolution operation for predefined blur filter or predefined sharpening filter. Like that. Okay, so in image processing domain, we normally use convolutions to transform the characteristic of the input image, and at the same time, that convolution is differentiable. Okay, so that's why we use the convolution when dealing with the 2D images, okay, to map them to the probabilities, okay. But transformer, their attention mechanism is also differentiable, and by experiment, we observed that that can better map 2D images into the probability. Okay? So that's why we are replacing previous CNN architectures to the transformer. Okay, and also there's no guarantee this attention mechanism is the best yet. Okay, so there could be another architecture that can replace this transformer actually. Okay, so this is actually the brief introduction about the transformer, and that is also constituted with the encoder and decoder structure. So when explaining about this transformer, you may see this type of figure frequently, and I will explain what they do later slide. But basically, this part is the encoder, and this part is the decoder. Okay. So that's actually composed of the encoder-decoder. So the input to the encoder, that's the input signal. And we encode the input signal into the feature. That's what encoder is doing. And then using the inputting this feature to the decoder, we output something. Okay, that's what decoder is doing. Okay. And before explaining about the transformer, I have to maybe first explain this RNN architecture. This is the architecture called as recurrent neural network. Okay. So RNN, recurrent. Okay. And this is actually the structure of the RCNN. So basically, this RNN is not RCNN. This is RNN. Okay, RCNN was the regional CNN, but this RNN is just the recurrent neural network. And this RNN is the architecture for processing the sequential data. Okay, so this is the input having time step t. Okay, so this could be some word sequence like I am a boy, right? So this is not fit to the image domain. Maybe if we are processing the video, then this could be first frames information, and this could be the second frames information, and this could be third frames information, and so on. Okay, so video information is this kind of the sequence data, right? But normally when processing one image, there is no meaning of this sequence. Okay, are you guys following this? But in NLP, the natural language processing, the data type itself is sequence data, right? So they frequently actually use RNN compared to the CNN architecture. So CNN, that's very good architecture dedicated to the image processing, right? But RNN, because the image is not sequential data, we normally not use this RNN much. But in NLP domain, the NLP researchers are frequently use this RNN. Okay. And what they do is this. So they first input the first word to this. You can think of this as the MLP layer. Okay, just one single layer do this kind of mapping. So W and B, that is some weight and access input. So this is the very basic layer, right? Maybe you remember this. This was the linear layer. So you can think this A component as some MLP, some linear layer or stacks of the linear layer. You can think of this A block like that. So this is anyways some MLP layer, maybe with some activation layers, okay? Are you guys following this? Okay. And then you can map the first word to their corresponding output, okay? Maybe let's say this is the translation application. Then we have to translate I to some French word. I don't know the French, but something in French. We have to translate that, okay? Oh, and then also we can do the same for the second word, okay, by using this A block, okay? And we can translate it to their corresponding French word, right? And for the second word, we can do that, okay? So first omit these arrows, okay? Let's first omit these arrows. We can independently do this kind of inference for each word, right? Okay, but maybe the performance might be, limited because we don't actually understand whole word sentence, but we now try to translate each word to each French word, okay? So the performance might be limited. So what this RNN is motivated was they actually want to propagate some information from the previous word, okay? So here A block is having some information about the first word, okay? And when inferring the second word, their output, we can get the second word at the same time the information from the previous word, okay? And then we can input these two and output the output for the second word, okay? And when inferring the third word output, we can also use the third input information at the same time, the information from the previous words, okay? Okay, that's what RNN is doing, okay, actually. So because it is the sequential data, they may have some, contextual information when processing the previous word. So actually these arrows are transmitting such contextual information, okay, to the later processing. Okay, are you guys understanding this? And if we draw it, we can also draw it in this manner. So this output is recurrently used as the input to the later processing, okay? So RNN, this is the RNN, but we can frequently draw the figures like this. Okay? So this is the recurrent neural network algorithm. But there's very critical weaknesses in this kind of RNN structure. Actually, the weaknesses, the critical weaknesses this RNN is having is let's say if this, we don't know about the length of the sentence, okay? And also it could be varied according to their data. Some sentence is composed of just 4 words, and some sentence could have more than 4, like 10 words, right? So the length is variable. So, but if length is more than maybe 20, what happens is vanishing gradient effect. So do you remember this vanishing gradient? So actually, in the first, when processing the earlier word, there was no vanishing gradient, maybe, but I mean, you have to supervise this output, okay? And when supervising the last word, if the sentence is very long, and when supervising this last word, you have to get gradient from every modules, okay? And you actually, by the chain rule, you have to actually multiply all the gradient in each module. Are you guys following this? And if you multiply, gradient are very small in scale. Actually, they are mostly less than 1. If you multiply the gradient value, which is less than 1, multiple times, like 20 times, then it simply goes to 0, okay? So that is actually the vanishing gradient phenomenon, right? So because of that, when you involve very long sentence, the RNN suffers, okay, from the vanishing gradient phenomenon. Are you guys agree with this? Okay. So to solve that problem, this later the LSTM, maybe this interchange it. LSTM architecture, long short-term memory architecture have been proposed. Okay. And actually what they do is they have some more gate, I mean some more sub-modules that can control which information you will forget from the previous architecture, and also we will which information you will retain from the previous architecture, and how much you will use the information from the current input. So actually you will learn this kind of sub-modules that control the information in the current input and also the previous layers architecture. Okay, so in RNN, we regard all the information from the previous layer and also the information contained in the current input uniformly somehow. And if it goes too far, then we experience the vanishing gradient effect. But in LSTM, we rather smartly adjust the weight of the previous layer's context and also the current layer's input, okay? So people say that this LSTM that is more suitable for processing the long-term context, okay? So that's the LSTM. So are you guys following this? Okay. And what they do is their architecture is like this. So we draw LSTM architecture like this. So actually in T-1 signal, there are 2 input and we output actually 3 things for the T frame. So when outputting these 3, we need these 2 information, 3 information actually. This X of T is the input in this frame, this input, and Y, this is the output, this output. And we have to transmit these two C and H, we get this from previous layer and transmit this to the subsequent layers. Okay, and we input the T's input and output the T's output. Okay. And this is the forget gate, and this is the input gate, and this is the output gate. Okay, and we will see the step by step. Okay, so this is the forget layer, and you may see that this f of t would be within the 0 and 1 range, okay, because they apply the sigmoid function in the last layer. This could be some continuous floating value, but because you apply the sigmoid after that, the forgetting vector would be ranged from 0 to 1. Okay, and this is actually controlling this. Okay, so from the C, which is the context kind of vector, retaining some information from the previous layer, and you multiply ft you just obtained from this for the ct minus 1. Okay, are you guys following this? And also you multiply this I of t. This is the input the scala controlling how much you will retain the input signal actually obtained from here. Okay, this I of t, that's also the value, the scala value, which is inside this range, because you apply the sigmoid after this operation. This I of t would be also the value between this 0 and 1. Okay. So I mean, the C of t is composed of this. Okay. And this is actually meaning you will multiply the weight for previous layers contextual vector, and also multiply I to a current context vector. Okay, and to make C of t by multiplying these two. This is actually mixing previous layer C information and current layer C information. And this tilde C means this from the input and previous layers HT minus 1, we multiply some weight and bias. This is actually the linear layer, right? This is the input, and we multiply some weight on that and add some weight and apply the tangent hyperbolic. So your information will be bounded to this range, because the tangent hyperbolic is, bounding the information within this value. So the C tilde will have the values from -1 to 1. But this might be some current frames contextual information. So you first get the C tilde from the previous layers information and current the input value x of t to get the C of t. First infer this and also multiply I of t, how much retain this C, okay, and multiply this forget, obtain this forget, and multiply this from this for the previous layer C of t, okay. And here what you will get is this, okay. So this, for this line, you will get this, okay, current frames T's context, okay. And this is multiplying CT minus 1 with the forgetting vector. So this is the kind of previous layers information, and this is the current layers information. You are somehow mixing those two and make the C of T, okay? The current frames information, okay? And you will transmit this to the subsequent blocks. And also what you will do for making this H, you also have to make this H of T, okay? And actually for doing that, you will estimate this H of T from the C of T we just obtained here, okay? So here you will apply tangent hyperbolic and also multiply OT, which is the controlling vector, how much information you will retain for the output dimension. So this is also similarly obtained when you get this I of T and F of T. So this is the output flag, okay? So you will get the same by applying the sigmoid. So this value is also in the 0 to 1, okay? And you will get this by applying some weight and adding some bias, okay? So you can also control how much information you will retain from the H of T, okay? So, and that information is transmitted to the later blocks, okay? And also, actually here, Y of T, that's also the, we also have the operation for this, obtaining this Y of T, but this is omitted. So this Y of T is also obtained for current, this is actually the current frames output. And for obtaining this, you will use the, anyways, the combining the input with this H and C to output this YT. Okay. So this is actually what LSTM is operating, maybe complicated, but basically what they are doing is improving the RNN in the aspect of the vanishing gradient. So RNN, we transmit all the information to the next block, and we use all the information from the current input. But these complicated things are doing that, how much you will forget from the previous layers information and how much you will use in the input dimension and how much you will use in the final output, okay? That's actually controlling the LSTM, and actually these weight vectors that calculate this IT, forget values and others are trained using the training data, so they can adaptively control how much you will forget, retain the input, and retain the output based on the data. You can estimate it from the data. Okay, so because of that, it learns how much you will forget and retain the information, and they are becoming robust. Okay, that's the LSTM architecture. Okay, are you guys following this? Okay. So maybe you can feel that because of this complicated unit, actually the LSTM is becoming robust than the, vanilla RNN architectures. But this is not that important. You will not use actually the LSTM or RNN in this class. Okay, this is kind of the background for we have to know when learning the transformer architecture. Okay, this is something we have to learn for processing the sequential data. Okay, RNN and LSTM, that's the model used for processing the sequential data. But in natural processing NLP, that domain, this RNN and LSTM were frequently used, but recently, maybe in the year of 2017, the transformer is proposed by some researchers in Google. And actually they replace the operations of the LSTMs using that paper, okay? And I will explain first the sequence-to-sequence model, which is composed of the LSTM architecture. So actually this sequence-to-sequence model is translating the English to other language, for example, the French. Okay, so they use sequence-to-sequence model to translate word sequence to the other word sequence. Okay, and actually that is composed of encoder architecture and also the decoder architecture. If we see the details of the, sequence-to-sequence model, then that is actually composed of the encoder and decoder architecture. And what they do is, in the encoder, they encode the inputs as the feature. Okay, so we input the English word, their sentence, English sentence, as the feature, right? And when doing that, what we do is we involve the LSTM architecture that can, that can process the sequence data, okay? And by input, when getting the feature for I, we get I and get no context from the previous block. But when encoding the feature for N, we can get something from the previous block, and you can use the current frames input. And also we propagate it to next block, and we input the next word and somehow merge the information from the previous block with the current input. And also we propagate it and get the last word. And this output is feature for whole sentence. Are you agree with that? Okay. So here what we get is the via encoder architecture composed of the LSTM architecture. We can get feature for this input signal, the sequential data. Okay, are you guys following this? And then what decoder is doing is they use both this feature and also using some input, they output this type of translated word. Okay, so this is their output. Okay, and what they do here is they first, at the first step, they don't have any input. Here, they only have this SOS, which means they will start the translation. So this is some reserved token, and it is saying that let's start the translation. Okay. If you input this, then combining that with the feature for English sentence, you will get the first output word for the French. Okay. And this is obtained. This is the first word in the translated output. And you will use this as the second input. And this second step, there is only two LSTMs. So the same LSTM, we can use the same LSTM recurrently to copy it like this, right? So I already told that we don't know the length of the sequential data. So this A block is shared to all the, all the words in the sentence, okay? It's same for here. This LSTM is having the same weight for all the word input. So at the first time, we input the starting token and it calculates the first translated word combining with the feature. And we can input the starting token with the first output. And then these two will output the second word. Okay. And combining the second word, using the second word as the third input word, we can get this third word. This is estimated. Okay, are you guys understanding this part? This is actually very important. Okay, so we this as the autoregressive inference. Okay, it is called as autoregressive because we somehow use previous steps output as the input to next step. Okay, so this kind of thing is called as the autoregressive prediction. And we also use the third word as the input to this decoder, and maybe we currently do this until we get this EOS token, which means that's the end of sentence. Okay, so we actually iteratively do this kind of autoregressive prediction until we meet this EOS, which is the end of sentence token. Okay, that's what happened in sequence to sequence model. So are you guys following this? 다 이해됐나요, 이거? And also, I mean, when using the LSTM, we can actually do this. We can actually achieve this when using the LSTM. But we can do the same using the transformer. So we can replace this LSTM part with the transformer. So this encoder, whole encoder is now replaced with the transformer, and whole decoder is now replaced with the transformer. Okay. And what transformer, their self-attention, or anyways, the attention mechanism, what they are meaning is, we actually calculate the dense relation between the input. Okay, so we input, I am a student, and LSTM calculate their features by using LSTM and sequentially getting the input and transmitting some contextual information to the next step. Okay, and the last feature vector, we will somehow encode all the sentence information. That's what we do here, right? But in transformer, they will input this all the word composing the sentence sequence all at once. Okay? We input this simultaneously. Okay, we do something to calculate the feature vector here. So here we have to get feature vector that encode this sentence, similarly to previous encoder, right? But what we do to calculate this feature is we calculate some relation between every word the sentence is having, okay? They calculate the relation between I and M, I and A, I and student, M and A, M and student, A and student. They somehow calculate, seeing all the relationship between these words and calculate one vector that encode this relation. That's actually called as attention mechanism. And later slide, I will show you the exact formula for this attention. Okay, but the concept is they calculate somehow the relation between dense relation between the input. Okay. And then what happens in the decoder is But one thing I missed is because they obtain this input signal all at once, we somehow don't know which word is first and which word is next. I mean, I is precede the M in sentence, right? But because we input this word at the same time, we somehow don't know which word is first and which word is next. But maybe you may think that because in this figure, this I is partially left to the M, right? And M is partially left compared to the A. So you may think that there is some that such ordering information remain here, but the transformer, they don't know about that because when inputting this signal to encoder, they somehow don't know, they somehow disregard their ordering, okay? But instead, the transformer, they have to have this positional embedding. This is frequently called as the positional embedding. And what they actually embed is this type of vector. So it is meaning that I is in the earlier part of the sentence, and M is in the mid position in the sentence, and also R is in the middle right position of the sentence. Somehow they have to make this kind of vector indicating the word location. And then what they do is they sum this positional embedding to the actually the features. So I mean, we do not input directly the I letter to the transformer, but we have to calculate some vector. So that we call this as the word embedding, which is the representation for each word frequently used in the NLP domain. They transform the word itself to some mathematical vector. So we call that as the word embedding. So this embedding is meaning some I feature vector, word vector, and we multiply this word vector with some positional embedding we created, and we input the summed values as the input to the encoder, okay? And the encoder of the transformer, they calculate the dense relationship between this input and calculate the feature vector for whole sentence, okay? And next, what they do in the decoder part is actually it is also not parallelly calculated, even though we use the transformer. We first do the decoding using this part only at the first step. We have to input the starting token and merging that with the feature information and getting the first word. And at the second step, we input this starting token with the first word we predicted, and then estimate the second word. Okay, and using this as the third input, we do this third inference, and also do the same for last part until we meet this end of sentence token. We iteratively do the decoding. Okay, this is actually same for this part, right? But the operation when doing this is different from the LSTM. What they do here is, let's say this part, okay? When doing the decoding for this, they densely see the relation between the input using the attention mechanism, and also they apply the attention with this feature vector and create the output. Okay. So I mean, encoder part, this attention calculating the dense relationship inside the input. They are called as attention, but they are called as self-attention. In the decoder, this operation is called as attention, but they are called as cross-attention. The difference is in the self-attention, they use the inputs only. Okay, that's why they call it as self-attention. But here, while doing the attention, they use the input. At the same time, they use the heterogeneous information from the encoder output. So that's why they are called as cross-attention. Okay. So this is actually the transformer. Okay. When you understand this, you may understand the transformer. And this is the exact operation for the self-attention mechanism. I will maybe explain this later. But you can maybe understand, if you understand this figure properly, I just explained this, right? Then this is actually same as this figure. So here you can see the input, and this is the embedding, which input embedding, which transform the word to some mathematical vector. That is kind of word embedding. We add the positional embedding here, right? And here we input anyways each word, okay? That's happened here. And here is the multi-head attention block, okay? This is actually calculating what I mentioned here, the dense relationship between the input. This is the self-attention block. And after that, we apply one linear layer. This is called as feed-forward network. This is a kind of MLP layer or the linear layer. And then you output some feature vector here. Okay, so that's happened in this part. Okay, you calculate dense relationship between input, that's the multi-head attention, and then you apply some MLP layer to make it into the feature. So that's actually happening here. Okay, and also here, this is the decoder. Okay, decoder. And for the output, we also have to change it, transform this as the embedding. And also we have to apply some positional encoding as well. So this part is actually same as inputting the output, okay? But I mean, this part, decoder, it operate in the autoregressive manner. So this is same for this figure. So shifted right. I mean, this is meaning that, okay, actually. So first, it starts with the starting token, but gradually increase the word inputted by using the outputted signals. Okay, and this decoder is doing also some self-attention here. Using the input vectors, it also does some self-attention, and using this signal outputted from the first self-attention mechanism, what you will do is mixing them using the features from the encoder. Okay. So here, what they do is actually the cross attention. So here, actually, we mix the information from the input and information from the encoder. That happens here via the cross attention mechanism. Okay, so you have to see these arrows carefully. Okay, and then we map it to some output by applying subsequent MLP and linear layers. So actually, that's the showing how we estimate the output for these signals. Okay, so actually you have to feel that this figure is same as this figure. Okay, are you guys following this? Okay, so this is the encoder part, and this is the decoder part. Okay, And I will explain this attention mechanism later in more detail. Okay, so and actually transformer in the encoder side, they regard the input as the non-sequential data. So they kind of encode the feature from the input sequence data parallelly by calculating their dense relation between words. Okay, so non-sequential, so their feature is non-sequentially encoded. So I mean, there is less probability to lose the information, no risk to lose the past information. Actually, that's the motivation for developing LSTM compared to RNN. Okay, but transformer is reduce such risks by parallelly calculating the input signals information. And also it could be very fast by applying some parallel processing method. So transformer, it exhibits better performance compared to the LSTM or the RNN. So it is actually replacing the RNN or LSTM. So that transformer is introduced here where the Google Brain researchers assert. So after this, NLP domain transformer becomes prevail. And also there has been some effort to use this attention mechanism inside the computer vision application. And that's one such example is this vision transformer. And the other example is this DETR, which is adapted to the object detection task. So later class, we will learn about this. Okay. Okay, for today, let's finish here. Thank you and see you in Wednesday. Okay.